It's a great pleasure being here with all of you, having the opportunity to participate in this data science conference and present some of my current research in the context of trying to transform neuroimages into very important, valuable knowledge to address some of what we consider some of the most important societal problems, which is drug addiction. And that's really what the field of data science is about, transforming data into knowledge. This is in collaboration with a team of psychiatrists, neuroscientists, and computer scientists. So let me start by talking a little bit about the problem of interest, drug addiction. Addiction manifests is a disease of the brain and manifests by craving for the object of addiction, then losing control over the use of this object, and making decisions that wouldn't be in our best interest with knowledge of that. Well, when we think about cardiovascular problems, we understand that they are a disease of the heart, or we are thinking about diabetes as a disease of the pancreas. With addiction, in the past, until recently, that with the power of brain imaging, we are starting to understand a little bit better what it means. It's been treated really with punishment. But addiction is a disease of the brain. The brain changes, and it's important that we are able to get back the brain to normal to be able to address addiction. Otherwise, we'll not be able to address it. Just with punishment or with the expectation of the development of willpower, we'll never be able to get there. What happens is that in the brain, when we get exposed to something, like in this case would be cocaine or the type of drug, we release a chemical called dopamine. What happens, dopamine, the release of this type of chemical transmitter, will lead to pleasure. The same in the does release in the part of the brain, in the midsection of the brain, in the limbic system, in the nucleus accumbens. So the release of dopamine would happen when we're exposed to other type of natural rewards, food, sex, money. But with drugs, just even a small exposure, the release of dopamine would be more than 10 times what happens or what we obtain with the natural rewards. So that leads to great pleasure. But these very large levels of dopamine start changing and impacting other parts of the brain, in particular the parts that are part of the reward system, and they control learning, judgment. So let me talk a little bit about cocaine, which is the focus of this particular study. So cocaine is an illegal stimulant, and it can be prepared synthetically, or it can be obtained from a plant called coca that grows in South America, primarily in Colombia, and it can be snorted, smoked, or inhaled. Just few statistics to share with you. This is from the United States. So the overdose deaths continue to rise every year by over 5%. 100 people die every day in the United States from drug overdoses. And we have 21.5 million individuals over the age of 12 that had some type of substance use disorder. And 1 in 5 is the number of young adults who are users of illicit drugs. So this is a very significant problem, but it's very difficult to address because the very high levels of dopamine in the brain start to damage, as I was mentioning before, the machinery in the brain. Furthermore, the receptors of the dopamine are also impacted, and they don't respond the same way. So we don't reach the same levels of pleasure and with the same amount of cocaine. So that leads to the overdose. We need higher levels because the receptors of the dopamine have been impacted. So this is the brain here. Here, this is the reward system right here in the limbic system. And this is where the dopamine gets released in the nucleus accumbens. So as part of the reward system, we also have the amygdala that controls anxiety, judgment, and then the hippocampus that controls memory and learning. So the high levels of dopamine would start impacting the amygdala and the hippocampus. As a result, what happens is that the pleasure obtained from the exposure to these drugs is remembered in the brain. And anything would bring those type of memories. Any type of environmental cues would bring memories of the pleasure linked to the exposure to cocaine. Furthermore, the amygdala, by being also impacted, would affect our judgment. And by knowing that even the exposure to cocaine would lead to consequences that we know they are not in our best interest, we still cannot control ourselves. So that's really the way it will work. The normal machinery, the metabolism of the brain has changed, has been impacted. And to be able to address this issue, we need to with different type of treatments that at this point we don't know what they are, but that's really the solution to be able to get the brain back to normal. And that's the reason why even individuals that have been able to successfully go through a recovery, 60% of them, they go back and relapse. The reason for that is that the brain is not back to normal. So the goal of this study is to be able to get a better understanding of how the brain of drug addicts have been damaged, have been impacted, so that way we can develop the right type of treatment to be able to get it back to normal. And the type of information that we are collecting is through two different mechanisms. One is called fMRI, functional magnetic resonance imaging, and the other one is DTI, diffusion tensor imaging. And we work with both. They do provide different type of information. The fMRI gives us information about the blood flow in the brain, and it helps us to understand how we react to different type of stimuli. The DTI gives us information about the white matter in the brain. The white matter is how the nerves impulses get transmitted in the brain, so it helps us to understand the functioning within the brain. What I also want to mention is that a part of the work that we are doing is not just in the context of the development of a therapy with different type of medication to help drug addicts, but we're also using literature, we're using education as a way to help, as a way for these individuals, for the drug addicts, to be able to find other ways of pleasure, to be finding other types of reward as a way of self-discovery. So in collaboration with the Commonwealth Attorney's Office in Virginia, I've been able to get an agreement where every year they send 10 drug addicts to campus to be with us. Instead of having jail time, we are using education as a way of self-recovery for them. Okay, so the two strategies, going back to our brain images, when we have this type of images, we either use them as a predictor or as a response, right? So we can use the brain image as a predictor to determine how the different type of, to study and analyze different type of clinical outcomes, or we can just use the brain image on its own as the response to determine how the brain, again, of a drug addict would be different than the brain of non-user. Here we are going to be focused on the later. We are going to be looking at these different images for addicts and non-addicts to determine what type of differences we observe, what parts of the brain have been impacted, and again, that can lead to the development of a treatment. So the images that we have, we are working with DTI, the white matter, are 3D. We have 3D images. So what you have here would be the projection along the different axes here of one of these images. So in this study, what we're going to be doing is looking again at the DTI images, and the main focus is to understand the differences, what parts of the brain have changed, and how they have been damaged. So we are working here with a group of close to 60 individuals. So we have 39 cocaine users and 19 individuals in the control. The cocaine users have been self-identified, but we also conduct a psychology study to determine if they are addicts or no, and we do have all sorts of information about then gender, ethnicity, education, cocaine use, and we also conduct other clinical analysis that leads to more information. The response variable is 3D for each one of them, 3 dimensions, a continuous variable between 0 and 1. And the goal here is to be able to make inference about the impact of drug use on brain activity. So, so the type of images, again, that we have are represented here. The top one, the top 3 images will be for a non-addict, and the bottom for an addict. And what we have here just slices. So again, this is a 3D response. And this would be the part of the brain. So we are looking at small or large differences between the brain activity for the non-addict versus the addict. So this is where the dopamine would be released. But part of what we're trying to understand here, beyond the reward system here, are there other parts of the brain that are also impacted? Okay, so this is a very challenging problem, primarily because of the magnitude of the data that we are working with and the type of inference that we are trying to make. So these type of images would have about 8 million voxels, 8 million coordinates for each one of our individuals in the study. So working with parametric models wouldn't be feasible. So the standard methods here, they either aggregate data, so we work with aggregated voxels in different parts of the brain, or we vectorize the image, so then it becomes a vector response, or we assume independence, we completely ignore the spatial structure of the data. And for the most part, the different sources of uncertainty in the models and data, they tend to be ignored. So what I'm trying to do here is to go beyond all these different type of assumptions to be able to work at the voxel level, to be able to make inference at each voxel to understand what parts of the brain in a very small or large scale had been impacted, but also taking advantage of knowing the spatial coordinates, the spatial structure that we have. So with that in mind, we are going to introduce here a new Bayesian tensor regression approach to be able to make inference about the impact, again, of drug addiction in the context of brain activity, making inference at the voxel level, and being able to characterize all the different sources of dependency and the uncertainty in the data models. With regard to the literature, so here we're going to be working with the response as it is, as a 3D problem, as a tensor. The literature that we have for tensor regression, for working with to conduct regression when we have these high-dimensional arrays is very limited. For the most part, it is being done either with the tensor as predictor or using frequentist approaches. Frequentist approaches in this setting, they would require a large N, a large number of individuals in relation to P. P would be the dimensionality that we have. That's certainly not the case here. Conducting this type of analysis, the image is incredibly expensive, and here having 60 individuals is already a very large number, but certainly N is very small in relation to P, that here would have the 8 million voxels. So here, again, we are going beyond the current literature to introduce this tensor regression in a Bayesian framework. But also, we want to propose something that is feasible and computationally efficient. So we need to introduce some type of sparsity or random reduction approach. Right. So a little bit of background. The response that we have is 3D, is an array in 3 dimensions, or what we call a tensor, a 3D tensor. So we look something like this, where we have the different coordinates of voxels here with the 3 coordinates. And the notation that we are going to use in this tensor regression model is going to be introduced next. So we have the response at tensor in 3 dimensions. So when a tensor is in 1 dimension, is what we call a vector. We also call that fiber. When it's in 2 dimensions, we call that a matrix. And here in 3 dimensions, we'll call it a tensor, a third-order tensor. So a couple of things that I want to make you aware. How we project a 3D image into a matrix, what we call matricization. So that can be done in different ways. That's what we call the mode 1, mode 2, or mode 3 matricization. So let me show you in the next image how that could work. So this is the unfolding of our 3D image into a matrix. So that can be done either using the top slices, so the horizontal slices. So if you look at what you have in the top, that becomes the first row. So that would be mode 1, the horizontal slices. Here, mode 2 would be using the lateral slices. So you look at what you have here on the side, then that would become your first row. And then mode 3 matricization would be using the frontal slices. So here, that would be what you have here, the front, that would be your first row. So at the end of the day, it's the same thing. It's different ways to convert or to project or to unfold a tensor of order 3 into a matrix. Then the other concept that we'll be using in our regression will be the product of a tensor and a matrix. So we call that the mode K, or the K-mode product of a tensor and a matrix. So what that means, this type of product, what that means is that from the tensor, we recover all those vectors, all those fibers of order of a mode K. So the mode K fibers would be all those vectors that have fixed all the coordinates except for the kth dimension. Those would be the mode K fibers that we can construct from our vector. And then we multiply using matrix multiplication, each one of all those fibers, all those vectors of mode K that we have obtained, and multiply each one of them by the matrix. So to be able to do that, you need to make sure that the number of columns that you have in your matrix will match the length of each one of those fibers or vectors. So that would be, again, the K-mode product of a tensor with a matrix. Okay, so with all that, we are ready to move into our tensor regression. So what we have here is each one of the images for each one of the individuals. So the image is a tensor of order 3. Here I'm introducing this in more general terms, where instead of order 3, this could be order M. So we have the image, we have the response for each one of the N individuals. So in our case, we have 58 individuals. And the goal is to be able to make inference, to estimate the betas, to make inference about the impact of different predictors on the response. And the predictor of interest here would be, is this individual a drug addict or not? And we have the residual components. So, but let's talk a little bit about the betas. The betas are also very high dimensional tensor themselves, because we want to allow the betas to change from voxel to voxel, and we want the betas to be able to be different for different predictors. We are also going to look at the ethnicity and other type of predictors. So then beta on its own is going to be another tensor, or even higher dimensionality than the response, because the beta not only change with voxels, they change with predictors. So if the response was of order M3 in our case, the betas would be of a tensor of order M+1. So we have the betas, and here we have the multiplication, the M+1 mode multiplication of the tensor here with vectors. The X would be vectors. We want to be able to allow for a spatial dependence. So this stochastic component is going to have a covariance in this high-dimensional setting, and we are going to allow dependence along each one of the m dimensions that we have for the response using a separable covariance. Okay, so the issue with this type of framework is that it wouldn't be feasible to implement in practice with the size of our response here. So what we're going to do is we are going to use an sparsity principle that I'm going to explain in a simpler setting, in a one-dimensional setting. So suppose that now our response is in one dimension, so it's just a vector for each one of the individuals. And this is the vector here. For each one of the individuals, you have something like this. And you have the predictor here and the response. So it could be the case that certain parts of the response, they are not very relevant in the context of the regression. They are not very relevant in estimating beta, because they are not impacted by changes in beta. So there is some component or some part of the response space that is irrelevant for the regression, or is what we call here immaterial to the regression. So those are the linear combinations of the response that such that they don't depend on the predictors, so they are not affected by changes of the predictors. And then we have the part that is relevant, the part that is material to the regression. So the idea here is to focus on what is relevant for the regression. So we want to be able to project ourselves in that space where we have the part that is material here for the regression. So there is some space of interest here, and we want to find the projection into that space. So the PO here is the projection into that space of interest, and the rest would be the complement. So here, this symbol means identically distributed, and this is statistically independent here. So we have the two spaces, the relevant one and the irrelevant one for the regression. And then again, this PO would be the projection into that space of interest. And then here, these are the bases. The gamma one are the bases of the projection into the material part to the regression. What we also expect is that there is some reduction in the dimensionality. So if we originally were in a space of dimension R, the projection into the material part for the regression would be of dimension U, with the expectation that U is much smaller than R. We also can write the covariance as a function of the variability that we have for the relevant part or the material part, and then the variance due to the immaterial part. Right, so here what we have, again, in the context of the bases, so these are the bases that have the information that is relevant in the context of the regression. So a few things here that we are assuming. So we are assuming that the span of the vector space, all the linear combinations of those components are included in the span of the bases, and that the projection into the relevant part versus the irrelevant, you have conditional independency there. So the goal is that when we are talking about the betas, which is entirely the purpose here, to be able to make inference about the betas, we have a significant reduction in the dimensionality. So if the betas were, as I mentioned before, in this 1D case, the dimension was R. Now we are going to be in a space of the here dimension U. So this would be the projection. So this is the basis that would take us into this relevant part to the regression. Okay, so now this is in one dimension, so we are going to take it to, yes, okay. We are going to take it to a much higher dimensional setting. So here we're going to do is the same thing for all the different dimensions. This would be justifiable in the context of working with the brain because there are going to be parts of the brain that will be not impacted by or affected by the particular disease of interest here. So we use the same principle for each one of the M dimensions that we have, where we find the projection that would be of interest along that dimension. So it's the same concept here. Then we put it all together, so we have the projections into each one of these relevant components or relevant parts for the regression along each one of the M dimensions that we have. So here we put it all together into this PY. So what we end up having here is these bases along the different dimensions, and then we have this is really a core tensor in the lower dimensional space. And so this could be interpreted as high-order principal component analysis, where you have the eigenvectors, and these will really explain how these eigenvectors relate to each other. Another way to interpret that is treating this as a Tucker decomposition, where we have this tensor in high dimensions, and what we are doing is decompose it into these bases and the core tensor that is expected to be in a lower dimensional space. Maybe we can visualize that with this image here, where this is where we started here, our tensor in 3 dimensions, and what we are doing, projecting that into a lower dimensional space where we expect this to be significantly smaller, and then the bases or the eigenvectors. So this will be the interpretation of what we are doing. So the way this is impacting our covariance, so going back now to the stochastic component, the residual, so we have dependence along each one of the M dimensions, and we can write the covariance or the dependence again as a function of the material variability and the immaterial variability. And equivalent representation would be writing it as a function of the basis functions, but then this omega here is a fully symmetric matrix in a lower dimensional space. So this would take us here to a dimension of U by U versus R by R. And again, we expect that the reduction could be quite dramatic, so maybe going from 200 by 200 by 200 to 20 by 20 by 20. That would be the type of reductions expected. So we're going to implement this in a Bayesian setting, so just briefly go through the type of prior distributions that we are going to use here for, in particular for the parameters of interest, the etas. This is the parameters going to help us to understand the impact of the predictors of interest on the response. We are going to use a version of a normal for tensors. So this will be the tensor normal, that is the vectorized version of the vectorized version of this would correspond to a normal distribution. And the other prior that I do want to mention is the one for the bases. That will be a matrix Bigman distribution. It's important to note, and the reason why I wanted to show you the priors is because this leads to full conjugancy, so it's incredibly computationally efficient. With regard to how we determine what is the final size of the envelope, so what would be the size of the U, what is the reduction that we are doing, we are going to be using DIC in this setting to determine what will be the optimal value of U, or again, the projection into the lower dimensional space. And an important contribution here is in the context of understanding the properties of this approach. So when we are working in this type of Bayesian framework, so we start with an a priori knowledge that could be quite imprecise through a prior distribution on the parameter space. And we update that knowledge according to the posterior distribution as we receive more information, more data. So the expectation is that when we get more data, we are able to improve the knowledge. The updated information that we obtain can help us to get closer to the truth. And that's the concept of consistency in the posterior. If we don't have consistency, that could really lead to very questionable inference. And the purpose of this study is to make inference. So it's important that we study consistency. The way that we study that is that this is a neighborhood. This is the Kullback-Leibler neighborhood around the truth. So what we want is that the posterior is going to be in a very small neighborhood of the truth with probability 1 as we get more information. So, so this is the concept of consistency that we are able to obtain in this setting. So the way we obtain the consistency here, okay. I'll wrap it up here. So let me just show you a simulation and just the results. So, so here, we have the setting similar to the one that we have introduced here in 3 dimensions. And what I want to show you is the impact on the inference, on the estimation of the betas using this approach versus other competitors. So here we have, we are going to be working with sample sizes of n, 100 and 400, and we are going to be working with different sizes of the envelopes. So the original data set is a 10 by 10 by 10, and we are going to work with different sizes for the envelopes. So, so just to show you the differences versus in using the approach presented here, where we characterize the spatial dependence in the residuals, and we allow the betas to change across the space, versus a Bayesian version of that without a spatial structure in the residuals, and then a wavelet approach here. So in the context of the computational effort, the proposed method here with all the spatial covariances would be very similar, this is in seconds, to the wavelet approach. But when we look at the MSE, how we are able to estimate the beta, so here we are looking at the MSE to see how, what type of inference we are able to make here. So we have the MSE, the standard deviation of that MSE, and the coverage. So what it becomes very problematic is that with the wavelet or with the standard Bayesian, without a spatial structure, the coverage is very poor. The nominal coverage here was 90%, and we're getting a 40% coverage. Furthermore, we can see the MSE here goes from 0.004 to 0.2, so an increase of 50%. The same thing when we look at the prediction. So when we look at the MSE in the prediction, similar results, very dramatic. You know, this is 15% greater than MSE with the Bayesian wavelet and 30% greater with the OLS. And I just want to show you the images just for the cocaine addiction. So we go back to our data. The original size of the image is to about 200 by 200. We're able to reduce it to about 20 by 20 by 20. That's the type of reduction that we have. If we look at the comparison of the proposed approach versus just using the Bayesian OLS without the covariance in the error component, we can see that for this data, we do need the proposed approach. You can see the dramatic reduction in the MSE and the mean square prediction error. And why I just want to show you just the inference. So here we have the betas. So we standardize the betas. So the betas divided by the standard deviation would be equivalent to the C-scores. And what happens is that with these large data sets, we have to be careful with false findings, with the false discovery rate. So what we do is along each one of the dimensions, we keep only the 10% highest significant values. And that's what we are projecting here along each one of the dimensions. So what you see in red are the ones that are significant. And we only keep those when we have at least 15 voxels together. So this is what we'll find, and what we are focusing in those that are red, and they correspond, what we have been able to find here, they correspond to areas that impact bipolar depression and also coordination, our coordination as well as judgment. When we do that without the covariance dependence, when we do the ordinary Bayesian OLS, we are not able to find significant values. Okay, so just to wrap it up, so what we are proposing here is an approach to be able to analyze large and complex, high-dimensional settings using this Bayesian regression approach, but implementing powerful sparsity principle that allow us to implement this in a very effective, efficient manner. And most importantly, that we are able to identify the parts of the brain that are impacted by addiction while we work on treatments to be able to treat it. Thank you.